Yeah, so it's just asking you to integrate an average function over some interval. So I guess this is problem one. So it's just saying integrate from this function that looks like x squared over x cubed plus, blah, let's call it 50 squared, right? And this is basically just screaming u to u pair. Because this is of a third power and this is a second, right? They differ by one. That's a really, really good candidate to try out u is equal to x cubed plus 50. Because then when you take du, the constant just disappears, and then you're left with 3x squared. So this 3x squared dx, and you get a perfect u to u pair. It works out very nicely. Okay, so I think that's the end. But for the first one, if it's the integral from, I don't know, some random a to a random b. By the way, can you see my screen?
Yes.
So if it's ln of u over u du, the idea here is, okay, you can try out a couple of things, but the one that came to mind after a couple seconds of thought was using U-Substitution. Or maybe it's called V-Substitution because the variable u is already being used. But the idea here is ln of u and 1 over u is a really nice pairing because the derivative of ln of u is 1 over u, right? So if we choose v to be ln of u and dv to be 1 over u du, this works out perfectly. And this just becomes, what does this become? This becomes just the integral of v, dv, right? Which just becomes v squared over 2. Exactly. And then when you plug this back in, this becomes ln of v over 2 squared, right? The power is not inside the argument of the logarithm, so you can't use the power rule. It's just squared.
About a different problem for that one.
Okay, gotcha. And then at this point, you just plug in your bounds, so not a big deal, right? The first problem should be pretty reasonable, I think. Yeah.
That's what I was doing wrong.
So then the next one is sort of asking about, if I remember correctly, I think this is problem 3. It asks you to take this function and integrate it and find, I think it said find all real b values, or something like that. I don't know. I'll make up some numbers like 1, 2, 3 or something. And it says to find all of the b values, such as this average from 0 to b, is equal to some number. I don't know, let's call it 10. And the idea here is that, okay, well, you do the integration for this thing. This turns into x plus x squared minus, what is this, just x cubed. And if you can think about moving the b to the other side, this sort of becomes equal to 10b. And you have to plug in the bounds 0 to b. And
what's 10 integrated? Sorry.
Why isn't the 10 integrated? Well, the integration only applies to this part over here, dx, right? The 10 is on the other side. They're asking you to set the average of the integral equal to 10. You see what I mean?
Okay.
Yeah. So
yes, I do.
Yeah, exactly. So then once you plug in b squared minus b cubed, this just turns into 10b. Well, this is seems slightly complicated at a glance because this is a cubic equation, right? But you could just note to yourself that p is equal to 0 as a solution, and then you can cross out a b from everywhere to get a perfectly reasonable quadratic equation. And then, so b is equal to 0 as one solution, and then you can find the 2 other solutions from cubics. As a kind of cute, just little factoid, it is technically possible to just compute all of the roots of a cubic directly. This was there's a quadratic formula for square, but there's also a cubic formula for cubes, and in fact, a fourth order formula for quartics. It just gets more and more complicated. But as it turns out, a neat fact of math is that it's not actually possible to have a general, like, fifth order version of a quadratic equation for fifth order polynomials. That's when it stops working. But they're not going to make you do a cubic, general cubic formula on the spot. So they give you this neat little trick where it can just cancel where the b can cancel out from every term, and then what's left is a quadratic that's easy to solve. Simple enough.
With your like the negative b plus or minus square root.
Yeah, the quadratic formula.
Would the b in this situation just be the 1 from the?
Yeah.
Just be 1.
Yeah. Don't get the. This b is just a constant or variable name, the b from the quadratic equation, negative b plus or minus the square root of b squared minus 4ac, this b is a
Yes.
different b from the ones over here.
It's the second highest power?
What's up? Yeah, it's the second highest power, or the first power. So really the one over here is going to be the b in the quadratic equation.
Okay.
Yeah.
Thank you.
If it makes it easier, maybe instead of calling it a b, call it like a z or something as a variable. But that's just a bit of a naming convention. The underlying math of the quadratic equation is still the same. All right, so for the next one, I was talking about something about population, right? By the way, to the other person here, we're recording, but if you have any questions, feel free to ask. I'm just a math hobbyist. I like doing problems with students and showing them how to solve their calculus more efficiently and providing extra little tidbits of math along the way. But I don't know, just making up some numbers here. 3000 e to the 0.01t. And I think it's saying it's starting at 1950 and looking at some endpoint, let's call it the year 2000. So t goes from 0 to 50. Right? The correspondence is 1950 is when t is equal to 0. 2000 is when t is equal to 50.
You just integrate that from 0 to 50.
Exactly. It's just a very simple average, right? And this might be the easiest problem on the set, I hope. But it's just a very simple exponential integral. And you just got to remember how to integrate your e, which, well, it's just its own self, right? But then the chain rule, you have to kick out a coefficient or divide by a coefficient. So pretty good so far? Okie dokie. So 5 is the integral of, I was thinking that it was really odd that you told me that you had just finished a homework on Saturday or Sunday and have another one due Wednesday, because that's pretty brutal, isn't it?
Yeah, that's what I was thinking. I was like, 3 days?
Right, but we'll, push through it really fast. But this ln of x squared was actually a little bit of the slightly trickier ones. The very first method I wanted to try, it wasn't too bad, but I mean, tricky as in, took 2 minutes instead of, 30 seconds, right? But the first thing I tried was u is equal to ln of x, where du was equal to 1 over x dx. And this did not quite work because even though you can turn this into a u squared, it's a little bit frustrating because then this turns into x du, right? X du. And there's not really a good way to get rid of this x. So
you can't use the integration by parts?
That's exactly what I used. Yes, integration by parts turned out to be make this problem totally solvable. Do you know exactly the method here? Or do you know the breakdown? I mean, I'm kind of hinting at it. What's up?
I thought you meant, what's it called? You could use integration by parts for ln of u and x.
Oh, I see.
U squared.
Once you get to that point, it's sort of like the U-substitution is already kind of a dead end here. The fact that we've already chosen the U-sub and there's not really any good way to express everything purely in terms of U, I would say give up on that method and try something else. You see what I mean? U-substitution works well when, let me put it this way, if there was an extra factor of 1 over x in front, if there was an extra factor of 1 over x in front, this would have been great because then this entire thing would have been du, and then there would be no x here. But unfortunately for us, this 1 over x is not there, which means that, okay, when you replace dx is equal to x du, you have this x left over that you just can't do anything with. So that was basically the first thing I tried. Didn't quite work out. Okay, let's try method number 2. Do you see an idea of how to split this up for integration by parts? I mean, I kind of just wrote it out this way. It's kind of natural, right? But let's take a crack at this and see what happens. So dv is equal to ln of x dx. By the way, for the student joining us, we're recording these sessions. They're just kind of problem-solving stuff to help you out with getting the gist of the homeworks. I work through the problems and sort of show you the problem-solving strategies, but we're not going to give out full answers here. They're kind of just designed to get you to figure out the homework faster and hopefully better than you would have otherwise understood it yourself. But okay, we're just going to write out the integration by parts. What do you call this? Like a mini little table? What's up?
I remember this, but can you explain to me why dv is equal to ln of x and not v?
Yeah, so I think you might just have a fundamental misremembering, or just do you just generally not understand what integration by parts is?
No, I
You
do.
do?
It's just I kind of struggled on it.
Yeah, so like, gosh, what you're asking me here is sort of like a fundamental question, but the whole point of integration by parts is to try to split up the original integral into a u and a dv, right? And the method, I mean, I can go through and explain how to do integration by parts and what the motivation for it is, but the brass tacks of problem solving is that you got to choose a u and a dv to hopefully end up with something nice. Like, would you
Okay.
like me to go through a quick primer on why integration by parts works in the first place, or no?
I don't mind it, but I have a question
What's up?
first. It's for the formula, it's UV minus the integral of v dv
VDU,
or v du.
right?
Then why is the dv important?
Why is
Just
the DV
define v.
important? Yeah, that's a good question. Because the idea here is that when we start with integration by parts, we start with UDV, and we're trying to change that into VDU. And to do that, we have to start by identifying a U and a DV. And from the DV, we find the V. Does that make sense?
Thank you.
Yeah. So I won't go through the derivation right now, but going from dv to v, ln of x dx is a very standard integral. And this is just the result, x ln of x. And what happens here is, well, just like you said, uv minus the integral of v du. What do we get? We get ln of x times x ln of x minus the
Times
integral of x ln of x minus x times 1 over x. And the reason
don't we
we,
have
what's up?
Oh, never mind. We could just use integration by parts again with the x ln of x.
Well, actually, we don't even need to. Or sorry, yeah. Well, the idea is that 1 over x and these x's cancel out. So all that you're left with is ln of x minus 1, which is a pretty darn easy integral, right?
Right.
Yeah. And just remind yourself that the integral of ln of x is a standard one. And it results in x ln of x minus x. It's not the simplest thing in the world, but it turns out that a
Remind
single
myself what?
what's up?
Sorry. Remind myself what? Sorry.
That the integral of ln of x is just x ln of x minus x.
Okay. Thank you.
Yeah. Any textbook
So
should
you
have that
just look
explanation.
over that.
What's up?
Do you mind going over like the proofs of why the integration by parts is applicable?
Oh, absolutely, sure. So let me just quickly finish writing this one out. So ln of x, what is this? Ln of x squared times x minus x ln of x minus this thing. Well, you can finish this off on your own, right? And just double check that my work and all the signs are correct. But that's that for that problem. But when it comes to just the explanation of integration by parts, maybe the best way to say it is, so you have let's say a function u and a function v, and they're both functions of x, okay? Let's say functions of x. The idea is that the product rule of this would basically be du over d, let's call it sorry, it's not exactly the derivative with respect to x, it's more like the differential. So basically we're taking the derivative of this thing, right? So this sort of turns into du times v plus v times du. Yeah?
duv plus v du. That looks like
This is the product rule.
f prime. Yeah, the product rule.
Yeah, I'm just sort of using some slightly, maybe some slightly sketchy notation. But this is more or less the same notation that you use in integration by parts with du and dv. But the idea here is this is just, this is the product rule. So if you just undo this product rule by integrating, what this essentially says is that uv is equal to the integral of v du plus the integral of Did I write the same thing both times? I did, didn't I? This one should be u dv. My bad. U dv. So what integration by parts is basically just reversing the product rule. uv is equal to the integral of v du plus u dv. And the motivation behind integration by parts is basically saying, maybe we're in a problem where u dv is what we would really, really like to find. Like this previous problem, u dv is what we want to find, but we really don't know how to calculate that directly. We really don't know how to calculate u dv directly, but we know how to calculate uv, and we know how to calculate v du, because it just turns out that v du is a little bit simpler. Well, okay, instead of calculating u dv, let's just subtract this and calculate the other side to find u dv. That's what integration by parts is saying. If these two parts are easy enough to calculate, that gives you a way to find out what integral of u dv is. Does that make sense?
Mhm.
Yeah.
How come sometimes you have to do integration by parts multiple times?
Why you have to do integration by
I
parts
know
multiple
you can't
times?
break them down.
Yeah, that's a perfectly reasonable question. And how do you put it? For situations like, I don't know, the integral of x to the cubed e to the x dx, if you have a problem like this, the idea is that every time you use integration by parts, you want to select u to be x cubed and dv to be e to the x dx. The idea is that every time you do integration by parts, the part that the u part sort of goes down a level in complexity, right? So instead of u, now you're doing du is equal to 3x squared. And if your v is set up nicely that it doesn't really gain in complexity, let's say it's a nice function like e to the x where its integral is just itself. The idea is that, okay, now so there's the uv term and then minus the integral of 3x squared e to the x. The idea is now that the thing you're being integrated is a little bit simpler than it used to be. You see that? Whereas this was a power of 3, now it's only a power of 2. And this is a good step, a good piece of progress towards integrating the whole shebang, the whole thing. Does that make sense? So here we would just do integration by parts again. So that's an example of why you need to do things multiple times. It's because every time you do integration by parts, it might make things simpler by, say, a power. And eventually you're going to want to get this power down to 0, so you can just end up integrating e to the x by itself. There are also other examples of times when you have to integrate it multiple times with a slightly different technique, but we'll get to that pretty soon. In fact, we're going to get to that now. The idea for number 6 is I is equal to, we're going to have some integral, right? And let's just call it e to the theta cosine theta d theta. I think this problem has maybe a negative sign here and maybe like a coefficient in front of the theta. But those don't really matter. Just be careful about chain rule, right? And I'll just do the basic problem without it. But the idea here is
those two functions don't go down.
What's up?
Those two functions aren't polynomials.
Right,
at least
exactly.
one of them isn't.
Both of them are kind of cyclic, right? Both of them are kind of cyclic. And this is a situation where, at first, we're not sure why integration by parts is helpful. But we're going to take a closer look. So e to the theta, right, when you take the derivative, it just turns into itself. Whereas with the sine, it turns into cosine, which turns into negative sine, which turns into negative cosine, which turns back into sine, right? So these are both cycles. But my claim to you is that this is actually going to turn out quite nicely if we just remember to spot a trick. So to start with, something a little bit different than the other problems is I'm just going to set I to be equal to the results of this integral. Okay, I is going to be the integral of e to the theta cosine theta d theta. And I'm just going to go charging in, even though I know the cyclic thing is going to be a mess later. I'm going to go charging in and see if I can make some progress with this. So u is equal to, I'm going to say u is equal to cosine theta, and dv is equal to e to the theta d theta. So then this just turns into du is equal to minus sine theta, and v is just equal to e to the theta. And okay, we just do uv minus, I guess it's minus negative sign, so it turns into a plus. Is that right? sine theta e to the theta, e theta. And remember, this entire thing is equal to I.
Isn't that, what's it called? The E? Oh, never mind. It's because they're together. So.
Right. So at a glance, this seems kind of scary because we haven't really made too much progress, right? Okay, my screen is freezing up a little bit, but I think we're okay now. So whereas before it was cosine theta e theta, now it's sine theta e theta. It's not really any better, but we're going to have to take a leap of faith and take another step forwards, okay? Because it just turns out that there's a trick that makes everything work out really nice. But we're going to basically do integration by parts again. And we're going to choose EU to be sine theta. So du becomes cos theta. dv is equal to e to the theta d theta. And v is just e theta. And what happens here is I is going to be equal to cosine. I'm just copying this over. Oh, was someone saying something? Cosine theta e theta.
He's watching a video. Or
Sure.
she.
And this is equal to sine theta e theta minus the integral of e theta cos theta, right? And at a glance, it's like, oh man, this sucks. We just ran around in a loop, right? This is not productive. We ran around in a circle. But what we notice is that this is a minus sign right here. And this right thing here over here is just I, right? This thing over here is just I.
Oh, so you can put minus I.
Exactly. So you can move I to the other side. And at this point, 2I is just equal to this stuff over here, which is nice because there's no integrals. And we're basically done, right? Plus sine theta e to the theta. Exactly. And now we can just solve by dividing the 2 over, and we've figured out what I is, right? And I, of course, was the original integral that we wanted to find. So this is a very, very funny technique where it almost feels like we kind of cheated because we didn't do the hard work out in the fields of actually figuring out what the heck this integral was directly. But we managed to compare it to itself and get an answer that way. I kept forgetting that this technique existed because I never had a good name to put to it, right? I recognize this technique every now and then in math, and I really wished I had a name. And it wasn't until pretty recently where I had a German friend that told me the Germans call this a Phoenix integral. A Phoenix integral. And I think this name is really cute. And the motivation for it is because as you're integrating this thing, the idea is that you find another copy of it, maybe a smaller copy, kind of rising from the ashes of integration. And the Germans decided to come up with a cute name, a Phoenix integral. And I thought that was very neat. But you see this motif a couple of times in physics too, where let's say that there was a coefficient in front of like here, or maybe a negative sign, or maybe a 10 out here. The idea is that with these kinds of problems, especially with e to the theta times a trig function, you get this cycle behavior where you have an I on the left-hand side, and you're going to have another I in here that might be like 100i or something, depending on how your chain rule comes out. But the idea is you should be able to move it to the other side and then just solve for I. And that's the idea.
Seems like a visual effect because like normally those things I don't catch.
Seems like a visual effect?
Or I mean like well yeah, something you have to spot.
Something you have to spot? Yeah. Like the very first time my teacher presented this to me in high school, I didn't spot it right away. I was like, wait a minute, what kind of blasphemy just happened here? But if you think through it a little bit, it seems perfectly reasonable, right? Once you can rewrite this to get rid of the integral and just write it as something in terms of I, well, at this point, it just turns into an algebra problem. I plus some terms minus some I. I is equal to this stuff minus I. We'll just solve for I, right? No big deal. And I think remembering the name Phoenix integral, I just hope that comes to mind whenever you see a situation like this where it seems to loop, but there's actually a solution. Okay, so gonna keep on chugging forwards. I think we can get this entire set done in we're at 25 minutes right now. I'm wanting to be done by like 30 minutes, kind of a speed run. But this next problem, w squared ln of w, I found was almost exactly the same. What did I do at first? I think I did integration by parts. And I said this thing is equal to I. And what I said was u is equal to w squared and dv is equal to ln of w. Again, we know the integral of that, that's w ln of w minus w, and this just becomes du is equal to 2w dw. Maybe there's a simpler way to do this than integration by parts, but this is just what I found out to be productive. So if you do integration by parts, this is I is equal to w squared times w ln of w minus 2. Well, this just turns into, because this is, the 2 comes from here, and we get a w squared ln of w minus w squared dw. And the integral of w squared isn't too bad, right? You can separate this into 2 smaller integrals. But the integral of w squared ln of w seems really, really nasty for just a second, until you realize that's exactly what we were looking for in the first place. So you can use the exact same trick, the Phoenix integral trick, to just call this thing I, move it to the other side, and solve for the rest. Seem reasonable enough?
Would you still have to integrate negative w squared?
You would, but that's not so bad, right?
No, not at all.
Not at all. Agreed. Yeah, you do have to integrate w squared. Yes. Yeah.
Oh.
It's a very cute trick, and I really like that. Maybe I'm just a nerd, but I really like the name Phoenix integral, because before I had learned a name, I kept forgetting the trick. But after finding a cute name for it, I never forgot the trick again. Okay, so the next one can be solved using some really obnoxious trig integrations. I think you could do something like turn this into 1 plus tan squared is equal to secant squared. But as it turns out, you don't have to use that technique yet. There should actually be something quite a bit simpler. But I think it just came down to choosing a good u to u pair, right? The idea is, if I rewrite this r cubed as r squared times r dr, suddenly choosing this thing to be u is equal to 16 plus r squared looks really, really nice, right? Because now du is equal to 2r dr, and as a reminder, just r squared on its own is going to be r squared is equal to 2, what is this? U minus 16. So, okay, this is r squared, this is r dr, and we know we have a good expression in terms of u or du for all 3 of these things, right? For all of them. And at this point, I think this turns into a pretty reasonable problem from there on out.
R squared equals u plus 16.
Yeah, I think it's a minus 16, but that's the idea.
Oh,
you see that?
Right. Sorry.
Yeah.
You're right.
So, yeah. I think it's a problem that resolves itself very neatly once you manage to find the right U-substitution. And that's kind of the thing about calculus 2, is that a lot of the times it just comes down to not quite luck, but integration is kind of more of an art than a rigorous procedure that can be boiled down to a precise set of steps. Sometimes you have to try things around to find the exact u that'll do the trick, or the exact u-dv pair that'll do the trick. But the hope for these videos is that they kind of, rewriting in a certain way will help build your problem solving or pattern recognition skills. Yeah, because when you have something like r cubed, rewriting it as r squared r sometimes is really helpful. And the reason I chose r squared r was because, well, r squared looks a lot like what's down here. So maybe we could just, changing it to u instead is sort of like moving the complexity from the denominator up to the numerator. Because what does this look like? It looks like u minus 16 times 1/2 du over the square root of u. And this is suddenly very manageable, right?
1/2. Oh, yeah, you're right. Because
yeah. Okie dokie. Next one we're looking at is also quite cute. E to the cosine t, sine of 2t. The first thing to remember is that this is a trig identity. This is a trig identity. And it certainly is. Or there's a relevant trig identity with 2 sine t times cosine of t. So if we just rewrite that, then the hope is that we either see a really good U-substitution or a really good, So I'm going to put the 2 out in front of the integral. The hope is that we see a really nice U-substitution or a really nice integration by parts. Any suggestions?
Sine 2t equals what?
Sine 2t
equals
2 sine t times cosine t.
times cosine.
Yes.
Okay.
That's the relevant trig identity. So if you're watching this at home, maybe pause the video and figure out try to see if you can find spot a nice U-substitution or U-dv pair. But for our listeners
U
here,
equals cosine.
yes, U is equal to cosine. Very, very good. So then what's du? That's just equal to minus sine t. So if we try to rewrite this as best we can, that's e to the u times, I'll move the minus sign out front. Well, that's just a du. And this isn't quite perfect. It's easy to solve immediately, but at this point, it should scream for you to use another trick. Do you know what that trick is? If you're watching at home,
by part?
Exactly, integration by parts. I've already used the variable u, but maybe you can choose maybe a z dv pair, right? And just figure out a way to use integration by parts to get this maybe u to go away.
C equals u, right?
Yeah, z is equal to u, so then dz is equal to du. And it sort of bumps down the complexity. It gets rid of the u variable, right? And then I'll let the reader take care of the rest at home.
Awesome.
But then I think we're approaching the end here. By the way, I think it said that there were 10 problems total, but I think you only sent me 9.
Because I got the first one correct, but I can send
Okay, gotcha. Yeah, I mean, I think for the sake of completeness, maybe that'd be good. But 9 theta cubed, I don't know, cosine theta squared, d theta. This is another one of those cases where, I don't know, let's not care about the constant in front. Let's not care about the constant in front.
Is that cosine squared?
Yes.
I mean cosine theta squared?
Yes, the square is on the theta, not on the cosine.
Okay.
But this, as always, I'm always advocating for tricks. And one of the things we did earlier was we broke apart the theta cubed, right? Because we saw a theta squared elsewhere, maybe this is our motivation to write it as theta squared theta instead. Do you see a trick for us?
Before and just have 3x squared, u is equal. Oh, that's the.
Do you see a good trick for us?
Yeah, u equals theta squared.
Okay, I think that's a very reasonable suggestion. So then du is equal to 2 theta d theta. Well, okay, theta d theta. That matches up pretty nicely right here. So then what does this become? This just becomes, okay, so I think I have to move the 1/2 out in front because du over 2 is equal to theta d theta. But this turns into u cosine of u du. And from there, everything else should be pretty gravy, right? You are going to have to use one more trick as before, but hopefully it's pretty manageable at this point.